In this few sections, we're going to learn a lot of really important facts that we're going to have to memorize. First off, we already know water can act as an acid or a base. Remember, we called that amphiprotic. What that means is that if you put water in with more water, it will do something called autoionize. It will act as both an acid and a base at the same time. And that means some of the water molecules will give up some hydrogen ions to some other water molecules, and you'll make some hydronium ions and some hydroxide ions out of it. This doesn't happen a whole lot, but it is there. It doesn't happen enough to make water be electrolytic, so it can't conduct electricity or anything like that. But it does mean that there are always some ions present in pure water. A little bit of hydronium ions, a little bit of hydroxide ions. Because of this, if we were to go and do the equilibrium expression of this, which would look something like this, it would include your products, hydrogen ions and hydroxide ions. Remember that hydrogen is the same thing as hydronium. Okay, same thing. We don't include our water because it's pure water. It's a liquid, so it's not included in our equilibrium expression. So our equilibrium expression is going to look like this: Kw, which Kw is called the ion product constant of water, is equal to concentration of H negative times concentration of H positive. Now, at 25 degrees Celsius, water always has the same concentration of hydronium ions or hydroxide ions. It's always 1 times 10 to the negative 7th. So you can see that is not very large at all, very, very small. But if I plug this number into my equilibrium expression, then I would get the value for Kw, which is going to be equal to 1 times the 10 to the negative 14th. And this wonderful little number here is one that you really need to know. It's called the ion product constant, and it is always the same thing: 1 times 10 to the negative 14th. We're going to use that a whole lot, so we want to be sure that we know it. One of the cool things about this is you can actually use this ion product constant in aqueous solutions. It doesn't have to be pure water. The ions will screw it up a little bit, but not enough to matter, so we usually ignore it, the effects that ions have on it. So we're going to see how we're going to use this thing a lot in the next few sections. Other things to know: in neutral solutions, the concentration of hydrogen ions is equal to the concentration of hydroxide ions, which we already said is 1 times 10 to the negative 7th. In acidic solutions, hydrogen concentration is higher than hydroxide concentration. In basic solutions, it's the opposite. Alright, now we're going to talk about pH. Now we already know the pH scale pretty well, I think. 7 is neutral, below 7 is an acid, above 7 is a base. One thing to note is we usually kind of stop the pH scales at 0 and 14, but there are numbers beyond that. You can have acids that have pHs below 0 that are like negative 1 or something like that. And you can have bases with pHs above 14. This is just where we've kind of stopped usually, but you may see some that are outside that range. Remember, the pH scale is a logarithmic scale, so that each time you go down a number, you're actually going down 10 times that or up 10 times that. Now the next section is new stuff about pH, and it is crazy important, so be sure to pay close attention and ask questions later on if you have any about this part. pH is all about the concentration of hydrogen ions, and there is a relationship between concentration of a mathematical relationship between the concentration of hydrogen ions and pH. And remember, I told you this was a logarithmic scale that's based on this equation. pH is equal to the negative log of the concentration of hydrogen ions. And I cannot emphasize enough how important this equation is going to be to you. So you be sure to get it down and make sure that you know it and that you can use it and know how to use it in your calculator. Now there's also something called pOH. pOH is just like pH, is a way to describe the concentration of hydroxide ions in the solution. And since it's just like pH, the equation's exactly the same too. It's negative log of the concentration of hydroxide ions. And if you took the pH of a solution and added the pOH of that same solution together, you always get the same number. You get the number 14. So every solution has a certain number, a certain amount, a certain concentration of hydrogen ions. It means it has a pH. And every solution also has a certain concentration of hydroxide ions. That means it has a pOH. And if you add its pH and its pOH together, then you get 14. These three equations together are going to get you a ton of points in the AP exam if you know them and you know how to use them. And they're not hard, so be sure you got them down. One thing that can be tough is when they throw these at you in the multiple choice section. Because how do you do logs without a calculator? Well, really, you don't have to. You can use the values that they give you to estimate pH values. All right. If you have a pH of 1 times 10 to the negative 6 for a solution, then that value there of negative 6, that value of 6 there, tells you that this has a pH value of 6. If you had something that had a concentration of 1 times 10 to the negative 5th, its pH is 5. 1 times 10 to the negative 3rd, its pH is 3. Now, if you have something that's like 1.2 times 10 to the negative 5th, that is around 5. 1.8 times 10 to the negative 3rd, that's around 3. But the further you get away from that 1 right here, then the greater and greater your estimate is getting. There are 3 different ways in which pH can be measured. You can use pH meters, which I'll show you in our lab. You can use acid-base indicators, which you have seen before. They tend to change pHs at very specific numbers. And whenever you use, the problem with the indicators, you have to use the right indicator, and they don't give you a range of pHs usually. They just kind of tell you you're in this spot, or this spot. For example, bromothymol blue, it's green at a pH of 7, and it turns blue when you go above, and it turns yellow when you go below. So you know when you're at 7, you know where you're above 7, you know when you're below 7, but you don't really know where you are. A pH meter will tell you you are at exactly a pH of exactly 8.2 or something like that. Okay, here's our list of strong acids. We've seen these before. We need to make sure we know them. Okay, these are our most important ones to know. We're right there. The others show up every now and then, but these 4 are probably the ones that show up the most often. We know that with strong acids, they have complete and total dissociation, so equilibrium lies far to the right. The pH of the solution is going to be completely and totally a result from the hydrogen ions from the acid. So the autoionization of water is really not going to matter too much with this. So finding pHs for strong acids and strong bases is really pretty easy. So let's take a look at this example here. It says, what is the pH of a 0.04 molar solution of HClO4? To do something like that, we just used that equation that we saw just a little bit ago. So pH equals negative log of the concentration of hydrogen ions. This is going to completely dissociate, so it's going to form 0.04 molar of hydrogen ions. So I plug this into my calculator, and you should go ahead and plug it into yours too, and make sure you know how to use this equation correctly. And I get an answer of about 1.4. Now when you get these answers, you stop and think about this. Alright, I can't count how many times I'll have students have a question like this, and the answer they gave me will be something like the pH equals 16. I'm like, is 16 a reasonable pH for a strong acid? No, it's not. It should be a really low number. Right? 1.4, that's a low number. Now, if I want to find the pOH, there's 2 ways to find this. The easiest way, though, is to remember pH plus pOH equals 14. So I just subtract that on out, and I get 12.6. The only tricky thing you gotta watch out for on these problems is every now and then they'll give you some sort of diprotic acid or some diprotic strong base, which we'll look at, or sorry, not diprotic, but whatever strong base that I'll show you in a little bit. When it does that, you gotta watch your concentrations more carefully. For example, if I had a 0.04 molar concentration of H2SO4, it's not going to form 0.04 molar H+, it's going to form 0.08 because its diprotic forms 2 hydrogen ions. Alright, so strong bases, remember it's pretty much group 1A and then group 2A from calcium down. Those are going to be our strong bases. Equilibrium is going to lie far to the right for those guys. POH comes completely and totally from the hydroxides in these bases. So again, these are going to be pretty easy to figure out. They will work almost the exact same way as the other problems. So let's take a look. What's the pH of a 0.028 molar solution of an AOH? I don't know. This is a base, so it forms OH ions, not hydrogen ions. So that means I can find POH, but not directly pH, so I'll have to go through some steps. So first I'm going to go ahead and find my POH, and then once I have my POH, I can use that to find my pH. So we have this as our final pH again. Stop and ask yourself, does it make sense that this is the pH of a strong base? Yes, it does. And then take a look at the next question. What's the pH of 0.0011 molar solution of CaOH2? This looks pretty similar, you know. The difference is that stupid 2. When it dissociates, it forms 2 hydroxide ions. That means that a 0.0011 molar solution of COH2 is going to form a 0.0022 molar solution of OH negative. And so you have to keep that in mind when you're plugging it into your problem. So why don't you go ahead and figure it out real quick and then check your answer. And so here is our final pH of our solution.